All right, let's jump right in. We're going to tackle a question that probably feels like a huge paradox, something you've likely wondered about yourself. If energy is always conserved, how come everything eventually just stops? Let's get into it. I mean, just think about your day-to-day life, right? Your phone battery dies. Your car runs out of gas. That hot cup of coffee you made, it gets cold. It really feels like energy is just, disappearing all the time. So what is actually going on?
This exact confusion was perfectly summed up by a first-year student on Reddit. They asked this question, and it just hits the nail on the head. It puts this fundamental law of physics in a direct fight with our own gut feelings. And today, we're going to sort this out once and for all.
So, to really get to the bottom of this, we've got to start by digging into that conflict, that clash between what we see with our own eyes and what physics tells us is an unbreakable rule of the universe. Okay, so for a really long time, scientists had this idea. They pictured heat as this kind of invisible fluid they called caloric. They imagined it flowing from hot things to cold things. And the key part of this theory was that caloric was conserved. It couldn't be created or destroyed. It was a nice, neat idea, but it was about to get completely turned on its head. Now, this kind of big shift in thinking, it doesn't just happen overnight. It started with some early ideas about motion, but then it got a massive push from this really cool observation. A guy named Count Rumford noticed that when they were boring out cannons, the friction created what seemed like an endless amount of heat. And all of this groundwork eventually led to the super precise experiments of James Prescott Joule in the 1840s. He was the one who finally put all the pieces together. And what came out of Joule's work was, well, a monumental rule for all of physics, the first law of thermodynamics. And it's pretty straightforward. Energy can't be created or destroyed. The total amount of energy in a system is always constant. It doesn't vanish, it just changes from one form to another.
So let's dive a little deeper into the work that gave us this foundational law.
I mean, just listen to Joule's own words here. You can totally hear the conviction, right? He knew he was on to something huge, something fundamental about how the universe is put together. For every little bit of mechanical work you do, you get a very specific, totally predictable amount of heat back.
And this number? This is the proof. In his famous paddle wheel experiment, Joule basically showed that if you drop a 772-pound weight by just 1 foot, the work it does will generate enough heat to raise 1 pound of water by 1 degree Fahrenheit. It's called the mechanical equivalent of heat. And it proved, once and for all, that work and heat were just two different faces of the exact same thing: energy.
Okay, but this brings us right back to our original paradox, doesn't it? If the total amount of energy is always the same, why does my phone still die? Well, this is where the second law of thermodynamics makes its grand entrance.
And I absolutely love this way of describing it, the running down principle, because it just makes so much sense. It's not saying the energy disappears, it's saying it becomes, well, useless. You can think of it like a one-way street. Energy is always moving from a concentrated, useful form to a much less useful one.
So here it is, the key difference. The first law is all about the quantity of energy. The total amount never changes. But the second law, that's about the quality of the energy. And that quality is always going downhill. The total amount of energy is still there, but its ability to actually do stuff for us is constantly decreasing.
And yeah, physicists have a name for this. They call it unavailable energy. It's basically all that energy that's been turned into something else, usually just low-level heat, and it's just spread out everywhere. It's not gone, it's just so scattered and diluted that we have no way to collect it and make it do any useful work anymore.
And the one big concept that we use to measure this unstoppable spreading, this degradation of energy, that's called entropy.
Look, you might have heard confusing definitions about disorder and all that. Just forget that for a second. The absolute simplest and best way to think about entropy is as a measure of how much energy has spread out. It's like nature has this fundamental rule. Concentrated energy just wants to spread out until it's evenly distributed everywhere.
All right, to really see this in action, we're going to look at something called an energy tracking diagram. It's super simple to read. The areas are just objects, like a hand or a spring. The letters stand for different kinds of energy. Arrows show where the energy is going, and we'll follow the energy from its starting point, the circles, to its ending point, the squares. Ready? Let's check it out. This diagram just lays it all out so perfectly. So look over on the left, in the circles. All the energy begins as concentrated chemical energy, that's the C, in the hand. Then, as the hand squishes the spring, that energy gets converted and starts to spread out. And by the time we get to the end state, in the squares, that initial energy has become kinetic, elastic, and, here's the key part, thermal energy, T. And notice how that thermal energy isn't in one place anymore? It's spread out to the hand, the spring, the air around it. That, right there, is entropy happening before your eyes.
But this whole thing raises an even deeper question, right? Why is energy conserved in the first place? Why is that a rule at all? Well, it turns out the answer is genuinely one of the most beautiful and profound ideas in all of science. See, these conservation laws, they aren't just random rules that the universe decided to follow. A truly brilliant mathematician named Emmy Noether figured out that they are the direct consequence of deep, fundamental symmetries in the very fabric of reality itself.
And this is the heart of Noether's theorem. It's this incredible link between symmetry and conservation. Just look at that first row. The laws of physics are the same today as they were yesterday and as they will be tomorrow. Because the rules don't change over time, because of this time symmetry, energy must be conserved. It's not a choice, it's a direct result. It's an unbreakable connection.
Okay, so let's bring all of this back home and finally, officially answer that question we started with.
We can now look at this question and answer it with total confidence. We have the two key pieces of the puzzle. The first law says the amount of energy never changes, and the second law tells us that the usefulness of that energy is always going down.
So no, that energy is not destroyed. It's not lost in the sense that it's gone. It's just been transformed and spread out so thinly, mostly as low-level heat, that we can't possibly grab onto it to do any work. It's all still accounted for in the universe's grand ledger, but from our practical point of view, it's become unavailable.
And that leaves us with one last, kind of mind-bending thought to chew on. If every single thing that happens in the universe makes useful energy spread out a little bit more, what's the ultimate fate of everything? What happens when it's all just a uniform, lukewarm soup of energy? Something to think about. Thanks so much for joining me.